very excited to have Sekhon here today in the seminar. My respect and admiration for Jas, who at the time where we were like a junior faculty at Harvard, both of us working on causal inference. Causal inference was not a thing then. Like you would tell people like working on causal inference, they would tell you like causal inference. What is the thing that you're saying? Like, so like we kind of gravitated towards each other in terms of the research and many other things and life. And it's great to have him here now. Like he's not Harvard anymore. He's at Berkeley, but he's moving, I heard. And it is going to be on the west coast, on the east coast, I think, like pretty soon. And yes, but right now, Jas is like a professor at Berkeley at the Department of Statistics and Political Science. And today he's going to talk about causal inference in the age of big data. Please join me welcoming Professor Jas.
Thanks for the invite, Alberto. It's great to be here. It's been a wonderful day. Hopefully I still have some voice left for the talk. As Alberto said, today I'm going to talk about causal inference in the age of big data. The talks from various different papers that I've written with various co-authors. I'll try to thank them along the way. First, I'm going to start with some background, which I know is a diverse audience, so I'll scene set somewhat. Although for this institute, I think it's probably most of this is known at some level. So if you're interested in causal inference, particularly causal inference about human beings, this is sort of like the golden age, right? The data that's being thrown off is unprecedented. There's some issues with that data in a sense that a lot of it is private and not publicly usable. And that causes some issues for the scientific community that we're going to have to work through. But it's unprecedented. So, we have a lot of administrative records on schools, criminal justice, IRS. For example, I had an economics grad student, Yotam Shemtov, who's currently an NBR postdoc joining the UCLA econ faculty, who has all of the individual school records merged to crime records and okay from the IRS for them to do the merge to IRS records for North Carolina for a 20-year period. So it's like, the joke I always say to him, he can go off and estimate the effect of class size on like crime. But that's literally, what he will do, like the network effects of that. And that wasn't even in his dissertation. So, and the thing about those data that's unusual and new is not the size. We've had large data sets for a while now, is that you have very fine-grained granular information on people. Right, so they're very long in terms of n is large, but they're very wide as well. So k, the number of parameters, is very large, and that induces a lot of inferential issues. It also allows you to do things that you couldn't do before. But that's like the width of these data sets is key, right? So of course, a lot of the usual examples from this come from large internet firms. So you have just tons of browsing, search, purchase data from massive online platforms. I'm going to talk. Some of the slides will be from data on that. And these are unprecedented. And we're still at the first parts of this because the Internet of Things is coming. That's going to throw out more real-time data. And of course, in the medical stuff, which I've worked some in, you have electronic medical records, genetic markers. And again, what makes them unique is just the massive amounts of covariates on K as well as N. So you can start doing things like, for one paper, I had all ICU admissions data for England. For a 5-year period for every single person. And you can then use that to gain, you also have randomized experiments, maybe you can borrow strength from them or what, or try to evaluate external validity. So this is pretty unprecedented. So these data sets are very wide, they're very long. And this just generates just a ton of inferential issues that we have not generally had to worry about before. And this talk is going to be on some of the ones, right? So from the policymakers, whether it's healthcare, whether it's government policy, whether it's firms, personalization of treatments is a really big deal, right? It's sort of like if the data sets gets very large and I have all this granular information, then I don't want to control my risk on some policy on average. I want to control it for subgroups, right? And that induces different kinds of methods and problems, right? The average risk is not going to help me that much. And then, if I just control the average risk versus subgroups, that could be the difference between my business surviving or not surviving, or a policy getting public buy-in versus not getting public buy-in. You want to model behavior, so, and I can use that to create markets. If I'm Uber, like, there's been a series of papers, like these ride-sharing companies, no matter you may think of their economics and how they treat their employees, have just resulted in just massive consumer surplus, right? It's not like they just replaced the taxi industry. Like Uber's revenues in the Bay Area alone are several orders of magnitude larger than the entire taxi industry was before Uber started, right? So he created this massive market for something that's not there and changed the asset allocation for automakers, right? And it's very data intensive how you do that. So the inferential issues are massive and plentiful. This data is very heterogeneous. It's heterogeneous in various ways. Partly it's heterogeneous because of the subgroups. It's also heterogeneous in a sense that as you get more data, its limiting properties are different than you think. Like one way of viewing, like, hey, what's statistics? It's like, hey, you get concentration inequalities that as I get more data, in a sense, the problem gets simpler, right? Well, the next 100 million users of online platforms are very different from the previous 2 billion, right? They're not going to be exchangeable. So in some sense, the heterogeneities it might actually increase as the data grows large. You might be able to make some assumptions to try to get around that, but the data is like super heterogeneous in ways that we don't quite think of usually. Policymakers then want to optimally allocate treatments, right? I have all this individual data on people. We're all going to become patients eventually in the medical system. It probably is not. If I tell you this drug works on average, that might be interesting, but you're far more interested in does it work for you, right? And then, and even if that second claim comes from data, for example, it's not a randomized trial, but an observational study, you might still want to hear and care about it because of the specificity about you that it's on. Now, this data and the ease to which you can analyze it has now like weaponized p-hacking. You can like optimize p-values, like literally in like large internet firms, you look at like how they look at their experiments. Most of them you literally get to search by p-value, by subgroup, and you're like, wow, that's a thing that you might want to control. And you look at the p-value as the experimental results are coming in, so you get to stop it when you want. So that's like a thing that's it's been known for a while, but it's usually controlled in the previous world by like hospital boards who look at it carefully. It's double blind. The board who decides this is not like the people designing the experiment to begin with. But now it's all together. So I have a set of work on try to get always valid p-values in finite samples, non-asymptotic arguments, even if you're get to stop the experiment whenever you want. Interpretability then becomes a huge issue from these, because in these complicated inference problems, people are throwing more and more complicated algorithms on them. In a lot of use cases, if it's not interpretable, the method will not be deployable, right? If it's like an online ad, and I don't really know what's making the algorithm go, if I get an ad that you were supposed to get and vice versa, like nobody really cares, right? The ad's worth some fraction of a cent. The harm done is like nothing. Like that's not going to stop deployment. In the medical setting, if it's like, hey, I'm going to do optimal allocations of treatments, but you get the drug I'm supposed to get and vice versa, no, people are not indifferent to that, right? So rules and so industry, as these ML algorithms get used to things that we care much more about, interpretability becomes a first order thing. Some of you probably know, but the EU's rules for interpretability and right to explanation. The things interesting about those rules is as they apply to algorithms are being held to higher standards than human decision makers. Human beings do lots and lots of things, and we don't actually have a clear description for why we did them. But the EU rules, as written, demand a level of interpretability for these algorithms that they just generally don't have. Like the key algorithms that run our lives, like say the newsfeed algorithm at Facebook, like no human being alive understands why it makes the decisions that it does. It's just too complicated. You can understand parts of it, but not the entirety of it. And how do you go about doing that is no easy task. So all these issues arise, right? So I mostly work on causal inference, and this talk's going to be causal inference in machine learning, like using machine learning tools to make causal inferences. And the causal inference application induces a set of problems that I'm going to go through this talk that most of what you have to spend the time fighting about is that in causal inference, we're trying to like predict something we don't directly observe. Right? If I have 1 million observations and you're asked to say, hey, tell me, is it a cat or a dog? In any given picture, I can easily tag if it's cat or a dog. That's like ground truth, it's known. And if I burn through that 1 million observations, I can get another 1 million pictures of cats and dogs, and I can know the ground truth of cat and dog. if I have an online experiment, like let's say I have 100 million people, which I do, for any individual, I don't know what the ground truth is on the causal effect, right? Because I know what the average treatment effect is with some precision, because half the people say got treatment, half the people got control. I can estimate that. I don't know what the treatment effect on any individual is. I don't know what the median treatment effect is without strong assumptions. So this induces, if I'm going to start now tuning an ML algorithm, how do I do that, right? And out of sample, I don't have ground truth. I have some estimate of truth. And that noise then becomes a very problematic thing. And the noise is significant even in massive data. Like the joke I would say when I got into this space is with huge data comes small effect sizes. In a sense that, if your data is large enough and your policy is going to be implemented on large enough people, very small effects become very economically policy significant. So you start worrying about them, right? So, to state the obvious, interventions apply counterfactuals, like what happens in treatment and control, which I don't directly observe. So I'm trying to estimate a response schedule and not just a direct prediction for the model. So that requires this validation loop's going to get complicated. I'm going to get into that. And then if I don't have a randomized trial and then and random assignment is confounded, right? Because say women take it out more than men, or people with certain traits more than others. Excuse me. More data doesn't solve that problem. More data just gets rid of the variance and I have a very good estimate of the bias, right? It's basically what I'm left with. And then a big one that happens here, because I'm mostly talking about targeting and heterogeneous treatment effects, is that predicting the outcome is often mistaken for predicting the causal effect. Now, whether it's political campaigns, I'll give you examples from that, or whether it's tech firms, if someone says, hey, I want to try to get a policy to get people to turn out to vote, right? Who should I target it to? Because I don't want to target it to everyone. Or I have an online ad that's going to get people to buy a book. Who should I target it to? In all these worlds, people go, oh, that's hard. Why don't we target to the people who are very likely to agree with me or very likely to buy a book anyways, right? Which is very weird, right? It would sort of be like a real example is like someone wanted to target an ad that was pro-abortion rights. And they have some experimental evidence that it works, and you're like, okay, who are you going to target it to? And they go, we're going to target to people who really believe in abortion rights and who believe it's an important thing. And you're like, well, that's weird, because they probably already know then, right? You probably want to target a different subgroup. The reason this applies is that I don't have a lagged outcome of the treatment effect, because I ran one experiment. So what do I condition my heterogeneity of treatment effect response to? When it's just the predictive outcome, do you buy a book online? Well, in my observational data, I know whether you bought a book last year or yesterday. So hence, you get this phenomenon, which you probably all have, that you bought something on Amazon and you're following around and getting ads for that thing, right? And there's a bunch of technical reasons that's happening, even if it's just a fridge, and you would think some algorithm knows you're not buying fridges often. But this lagness of it comes up. So if I want to, so the short answer of this is if you ask me to go get predictive covariates to predict your future outcome, that's a much easier ask than you ask me to collect covariates that's going to predict the future causal effect. The reason being, if I know nothing about your problem and you go, give me a good predictor for your future behavior, I'm going to go, I don't know nothing. I'm going to look at your lag behavior, right? Oh, you're going to vote next time? Did you vote last time? Are you a Republican or Democrat? I don't know. What were you last year? Right? Or did you buy a book on Amazon? What did you do last year? Right? I can always do this lag game if I don't know nothing else. For the heterogeneous treatment effect thing, it doesn't quite work because I don't have that data, right? So the other thing that's thrown up, because we have this vast amount of data, right? We're applying these more and more complicated algorithms whose theory is very poorly understood. And I'm going to be talking about some of them. In the class I'm generally going to be talking about Rosanna Forrest is the theory is better understood under theoretical moves that basically make you ignore the algorithm. Which is kind of funny. But you get, so you have to make an argument, right? And there's two kind of arguments we usually make, and then they're very, very different, and people confuse them. It's confused in the academic literature, it's confused at tech firms, it's confused all over, right? And I'm taking this division in some sense from Leo Breiman's famous essay on two cultures that you probably want to read. And one argument, the standard argument is from statistical theory, it works because you have relevant theory that tells you how it goes. And this is good, and it's good, and I'll give you some Minimax results that I'm going to tell you don't actually tell you what happens when you estimate Kate and finite data. And finite data, I mean tens of millions of observations. And hopefully it's not like what Breiman disliked, assume the data generated by the following model because they find it tractable. So that's one set of arguments. Another set of arguments is, oh, it's a test trailing loop. I don't know what it does, but I just have lots of test and validation data. and it kind of works, right? And this is not like a bad argument, right? Deep learning did not win because we have a good theoretical understanding of it. We don't. We know stochastic gradient descent is a regularizer. Exactly in what way it's a regularizer, who knows, right? We know dropout has something to do with the nuclear norm as well. Exactly how, when, I don't know, right? People don't know. It won because it actually worked on test beds. And then the theoretical understanding is like following behind on it. And you don't want to get confused for why you're doing one of the others. And the confusion is very common. It's gone on for a very long time. It's a famous quote that I got from Definetti's probability book that he attributes to Poincaré on the normal distribution, which he says that, you know, experimentals believe in normality because they think it's a mathematical theorem, central limit theorem. Mathematicians believe because they think it's an empirical fact, right? And that's like a funny thing, but it's not a world you want to like kind of get to. The normal distribution is an interesting case I'm not going to get to because a lot of tech firm problems have very, very, very fat tails. It's not actually clear if central limit theorems kick in, or if it is, at what rate they kick in, because the tails are super, super fat. Like for most online ad experiments, 99% of your data is 0, right? So 90% of people don't click it. 90% who click it don't buy it. So, and then the people who buy it have a very fat tail in terms of the amount of the revenues you get. Now, if you want to figure out on this ad, is it revenue generating? It's actually a very interesting problem. It's a very complicated problem. Right. Okay, so an example that's going to bring this together is that this plot is based on 278 different experiments from a very large internet provider. Each experiment has a sample size of 100 million people, right? Now you take those experiments and you estimate a whole bunch of different subgroups, right? And you have, and you estimate very different, and you're estimating all sorts of different treatment effects. You're estimating 25,000 different treatment effects, right? Just difference in means estimator. So you can imagine I have some experiment. I'm going, what's the effect for men or women? People use the iPhone versus Android. The list goes on. You have 25,000 of those treatment effects. Each one of them is powered as a sample size of about 1.1 million people, right? You can do the math in your head and go, hey, there must be replicated people here, because now we're talking billions. And you're like, yes, there's replicated people, and you're ignoring it. So what you're plotting here is the difference in means estimator standardized across all those experiments, right? And that's your density. This comes from a paper with Yotam and I. This paper, the only reason we can get this data out from this internet firm is this paper is a very theoretical paper. So the paper is giving you a consistent variance estimate for the sample average treatment effect for the treated, which is point-wise identified, unlike the variance estimator for the average treatment effect overall under the name and model. For those who know what that is, you don't have to, it's fine. But you could get it out because that's such a boring paper, no journalist could possibly be interested. So the tech firm's like, fine, you can get it out. I can't tell you what the data is. But the key point about this is, hey, most of your treatment effects are 0. They're so 0, that's not like, hey, I should start with a prior of 0 in a normal distribution. It's like double exponential. It's like Laplacian here, right? So if I'm going to do any further experiment, I'm going to go estimate treatment effects for subgroups, I probably want to like take 0 as a very serious thing. And I might want to pick a method that either formally shrinks to 0 or has properties to find 0. Right? So when you need an example that you can get lots and lots of data, we don't have to have a complicated discussion, is this good or bad prior. I can just go to their databases and pull these. So I want to use them in some way. And I can't talk about which all those experiments are, so I have to talk about other experiments. So the data I'm going to talk about is from Get Out the Vote experiments. So oddly, that's public, because in the United States, whether you vote or not is a matter of public record. For whom you vote is private, but whether you vote or not is public record. I can go look it up. We have databases, and I can like go search. It's kind of creepy. When I lived in Berkeley, my neighbor would go, hey, Jazz, you didn't vote last time. And I'm like, oh, great. I have to have this conversation. It's not creepy at all. But that's it. So a very particular experiment that was done, and after there's a lot of these Get Out the Vote things went private, became secret because it was so powerful. It's usually a thing that happens in science. When you have a very good result, it becomes very valuable, and then it goes quiet. This one was a social pressure experiment done by Alan Gerber and Don Green, who were at that point were at Yale. What it is you send a mail, it's a postcard to people. All you do is send a postcard, increase turnout 8%. It's massive for the postcard, right? So you can imagine political campaigns are interested because they'll just target it to voters they like. So you send a postcard, and they'll say, it looks very boring. By randomized experiments, by the way, it shows you don't actually want color and flash. You want a very boring, official-looking document, right? And you'll say, hey, what if your neighbors knew whether you voted? And then you have some text, please vote. This is the voting history of you and your neighbors. We're going to update it after the election. So you have people's names, right? You have whether they voted or not in the past and blanks for the future. and said, we're going to update and send it to all you and your neighbors. So some small percentage of people got upset, but it has a massive effect, has an 8% effect on turnout on average. The thing about this design, and it's very common now in these kinds of large experiments, is that the control had 200,000 people in it. Treatment is 30,000. So treatment is much smaller than controls. You can easily see how this happens a lot. It happens at tech firms. That control is just whatever you do anyways. And I'm going to get hundreds of millions of observations on that. And treatment is what I get to pull off. And treatment's going to be much smaller. So I have a massive imbalance between control and treatment. I'm going to exploit that in my estimators in a sec, right? So if you do that, and the original authors just wanted to estimate the average treatment effect overall, I want to estimate the conditional average treatment effect, which I'll formally define in a few slides. Currently, you can think about, oh, what's the treatment effect conditional on some observed covariates? Right, well, you'll find in this experiment, which has a massive treatment effect of 8%, the outcome 0, 1, did you vote or not, that this is the conditional average treatment effect, you can find that, hey, actually there's huge heterogeneity. That most of the treatment effect is in this subgroup. There's not much effect here. There might be some evidence for a negative treatment effect for that subgroup. Oh, you should probably just target the treatment here and save yourself some money. I'm going to do that. The shading here is what proportion of that bin is significant in an hypothesis test. And getting confidence intervals for this kind of problem is not at all simple, the ones that actually work. We'll talk about that in a sec why. Right? But that's not very interpretable. You're not going to convince any campaign to do that because they'll look at this histogram and goes, what are you talking about? Right? This is crazy land. Right? What they're going to want is things like that. It's like, okay, I'll break this down. I'll break it down by the same information in the previous slide by the voter proportion in the past. So this is your voting history. You never voted. You vote all the time. You vote in the middle somewhere. Right? And that's my density of my estimated treatment effect. And you're like, hey, don't target people who vote all the time. Don't target people who vote never. Vote people in the middle. Skill testing question, why on the Democratic side, if I tell you don't target people here, people get upset? Right? Because these people are then going to be people lower socioeconomic status and the demographics. So people are like, hey, you're not targeting them. And I'm like, yes, but I want to win an election, so target them. Right? But you can just see that off the slide. There's also now these are correlated data, and so you can there's other covariates that might be proxying this, like age or something. Another way of seeing it is you can see it in these box plots in terms of the median treatment effect, the interquartile range of the treatment effect. All right, so how do we get that? And how do we get those confidence intervals? You can do this on lots and lots of other data. That was massive. This is a small data set. There's a very famous data set from two graduate students of mine, Dear Brockman and Josh Kella. David's now at Stanford GSB, and Josh is now at Yale. This was this famous thing on if you knock on people's doors, can you get them to change their views on trans rights? The original paper of this turned out to be published in Science, but was fraudulent. They found the fraud and actually did the experiment right. This one also had a massive effect, and they found it's tuned to some subgroup. This one the policymakers had a great concern that there was a negative backlash, right? And you don't find any evidence of that, right? There was priors of it. They did the same kind of treatment on abortion stigma. There's no treatment effect basically. The average treatment effect was 0. You're not get a 0. So how do you do this, right? The first thing to realize, estimating treatment effect heterogeneity is a very bad problem. It's a hard problem. It's a hard problem for a variety of reasons. One is p-hacking is a big problem. If what I let you do is chop up your data into 1,000 subgroups and let you pick, well, wow, that's to try to protect your type 1 error is kind of tough, right? You're going to start data mining. You're going to go through it. And it's going to be rough. People have done pre-analysis plans to say, and this happens a lot in medicine, oh, you have to tell me what subgroups you are going to look at and only look at those, and I can then do various corrections. It turns out even in medicine, people actually violate their pre-analysis plan on a regular basis, and reviewers are too lazy to check it. There's a game. There's a dynamic game between the policy we make and researchers. So pre-analysis plans have come into various fields like clinical medicine, political science has it, econ now has it, and development experiments. So pre-analysis plans have gone much longer because people then put every analysis they want in it. So you get an interesting game. And then a lot of the methods that you use don't have known statistical properties. And what I'm going to emphasize in heterogeneous treatment effect is the asymptotic theory we have, particularly for the more complicated methods we want to use, is very poor guide in finite samples. I'm going to give you a set of estimators that the same minimax rates. Right, under a set of assumptions. They have very, very different finite sample properties, I think in a way that's pretty intuitive. Right? So the minimax results, we can get them for these black box models, but they might, for the conditional average treatment effect, they don't reveal as much as we'd like. I don't see the same problem when it's the average treatment effect, right? Because that's like one parameter, so an average. The conditional average treatment effect is this vector, so there's like a reason about that that's going to make it tougher, right? And the problem is a lot easier if we make simplifying assumptions of what that vector looks like, right? Okay, so just some notations. We're on the same page, right? So the thing we'd like to do, but we can't do, is estimate the individual treatment effect. Call y sub I1 your outcome under treatment for individual I, and y sub I0 the outcome for individual I under control. And these are conceptual things, right? This is what would Jane voted or not if I knocked on her door. Would Jane vote or not if I didn't knock on her door? Only observe one of the two. Call that d sub I, right? And call tau hat sub I the estimator for d sub I, right? So what I want to do here is estimate the conditional average treatment effect for all units of covariates equal to x sub I, right? So that's this. I'm going to just expand out the expectation of this and want to make a comment because lots of different fields are interested in this problem now, and there's some confusion, right? If I decompose the mean squared error from this thing, what you'll see is it's two different parts, right? One is the estimation error. Imagine that I only have one x. X is gender. Are you a man or a woman, right? The first thing is, and you want to estimate the conditional average treatment effect for men. Well, the first part is just estimation error. So that's going to be the mean estimate that I have for men and the true mean estimate for men, right? And if it's the simple problem that I just gave you, well, that's easy. The bias of thing's going to go down to the rate of n, right? Like my variance estimate goes down to the rate of square root of n. Getting correct inference is very easy. But note, even in this case, there's an approximation error that will not go away. That approximation error is, oh, if an oracle told me what the average effect for men is of some drug, and I'm a man, I listen, okay, and there's no error there, but there's a massive error between me and the average effect for a man, right? And that could be very large, it could be very small, it kind of depends, and the observed data does not distinguish it, right? I have to make some very strong assumptions to go forward. Particularly from the CS literature, there's a bunch of papers saying, hey, I can estimate the individual treatment effect. And the thing is, well, that requires then very, very strong assumptions. The thing that's going to happen for this part when we do the conditional average treatment effect is we want to do this using these modern ML methods. Well, now their bias doesn't go down 1 over n. Their bias goes down, say, square root of n. Their variance estimates, even under various complicated things we do, sample splitting, et cetera, that we'll talk about in a sec, also goes down square root of n. Your bias is not ignorable, the first order, right? Bias is a very hard thing to get a hold of in the data. It's even made harder here because I don't even know what ground truth is in a holdout set, right? And I'm going to estimate a vector parameter, right? So for the asymptotic theory to be a good model for what's actually happening in even large data becomes quite problematic. Right? But we're trying to go off and estimate this thing, right? So the first part of this talk, I'm going to walk you through some meta learners for estimating the conditional average treatment effect, which is to say I'm going to estimate that the conditional average treatment effect, I'm going to decompose it into subregression problems, right? And you can use any regression estimator you want. You can use a neural net, you can use random forest, you can use a k-means, you can use OLS, you can use whatever you want, right? And I'll turn it into a conditional average treatment effect estimator. Right? And then I'll flag here, I'll show you stuff later that the base learner that you use will greatly affect its performance in finite samples. And when I keep saying finite samples, I mean it half as a joke because my finite samples are very large, right? Even when they're tens of millions, the finite sample behavior really matters on what the actual learner, how you actually do the estimation. And that's another gap between us and the theory. The theory is all done in minimax rates, ignoring key properties of the actual estimators that you're doing. Right? Okay. So what are some of these? I'm going to walk you. There's many, many of them. I'm going to try to get through a talk, try to talk about some of these. I'm happy in the Q&A to talk about many more. Right? Okay. So first note, if I'm going to estimate the conditional average treatment effect, that can just be decomposed with the linearity of the expectations operator between the expectation what I'm especially under treated minus control. Well, that leads to the oldest estimator in the literature for estimating heterogeneous treatment effect, which is called the T-learner. I'm going to say for 2. And I'm borrowing the name for from work from Susan Athey and Hito Imbens. So I'm going to split the data into control and treatment groups, right? I'm going to estimate 2 different regression problems, right? I'm going to estimate these 2 conditional expectations, and then for my K, I'm just going to take take a given X, put it through my model for treated, put it through my model for controls, just take the difference, right? And I'm going to do it. And this thing under a set of assumptions hits the minimax rate. All right, I'm going to do something different, which also hits the minimax rate. under certain assumptions. It's like, oh yeah, I'm going to assume the treatment is like any other covariate, right? And then for the time being, just assume this is a randomized experiment, that there's no confounding, right? So that's not a problem. Trying to estimate the propensity score or something is just not a problem here. All right, so it's the S-learner because it's a single model. What I'm going to do is I'm going to add treatment in as a covariate, right, to one model. I'm not going to divide treatment and control up. And then I'm going to just, for a fixed x, do a prediction setting treatment on, just treatment off, and just look at the difference. And that's my estimate, right? And they'll both have the same minimax rate. They're going to behave very, very differently, right? To give some intuition for how this is going, I'll work with trees. So I'm going to talk about like random forest algorithms. Is that, hey, the first thing, like the T-learner, this two thing, is sort of like if I split on treatment and control in the top node. If I ran a random forest, but just insisted in the top node, I just split on treatment and control, right? Because after that, it's like two separate models, right? So it's very little pooling. It's pooling very little information from treatment and control, right? And that's going to have certain features, right? And the alternative is going to be I'm going to not force a split. I'm just going to include treatment like any other variable, right? So then I might split there. I might decide to split treatment there. I might decide to split treatment there. I'm going to call that the S-learner because it's a single model. I'm just going to like, you can just think intuitively here. Say treatment had no effect. Which of these two would you rather do? If I just told you treatment has no effect, which one would you prefer? S, right? Because I want complete pooling of the data. And then the algorithm's going to go split on treatment sometimes just by random chance, but that's not going to be good for it, right? All right, there's a third things you're going to do. This causal force by Varga and AP. What it does is says, all right, what I'm going to do is I'm going to force a treatment split at the very bottom, right? And then I'm going to try to force that split to estimate the conditional average treatment effect. All right, that's going to have certain issues that we can discuss. And then we'll all hit the minimax rate. They're going to perform very, very differently, right? Okay, so and the key thing, just the theory to go through, I'm going to talk first version of this for random forest, is that we're going to use honesty, which goes to Pvalue and Sornay, and I think Varga and AP were the first ones to actually have code for this, right? And it's a lot of similarities between this and sample splitting and cross-fitting work done by people here, right? The key idea in the forest is I take my sample, I chop it in for every bagged sample, I chop it in half, I grow a tree in one half, then I delete its y's, take the y's from the other half, put them in. Do the reverse of the other half, and then take the average, right? The reason the theory now goes through is I have now made my tree and y independent by that sample split, so I get to like ignore the complexities of the random forest algorithm, which you cannot theoretically analyze after the first split. So it's a little comical, but we can make the theory go through then. And then you can get asymptotic normality, you can get results for a variance estimation, and so forth. Right, okay, so then there's a different meta algorithm I'm going to tell you. It's going to call the X-learner. I'm going to motivate it this way. All right, so imagine you have a very unequal sample size, right? Treatment and control have very unequal sizes. And I just told you this is going to be a very common thing. It's true in the get out the vote. It's true in these online experiments. So the blue is treated in X as control. And if I'm going to run like a function through these, right, and say I'm doing the T-learner, it's easier to think about. Well, I don't have a lot of data here. I probably just want to run a straight line, right? For here, I have a lot more data, so I'll probably just estimate this function. This is fake data. So it's like mostly this talks real data, but this is fake data, right? So I don't want to do that. Right? You see why, right? I have a lot of data here. I can fit a more complicated function than there, right? For like treatment and control. Now I'm going to take the difference. The problem is my conditional average treatment effect function, which is the difference, now ends up being quite complicated, right? In this precise case, actually, the true treatment effect is the dotted line, right? But the game that you played that was problematic is I fit a simple model for treatment because I didn't have much data. I fit a very complicated model for control because I had a lot of data. And then when I took the difference, I forgot about this fact that I didn't have a lot of model data for treatment, and I didn't target the conditional average treatment effect function directly. Ended up with a very complicated function that I don't have the data to support that estimation on one side, right? So that's what I did, right? So here's an alternative thing, which under one set of assumptions of, say, treatment and control is balanced, is the same minimax rates of the previous two. Under an assumption, as we'll see, that the data is very imbalanced. So if, say, I have many, many more controls than treated, it's going to have better minimax rates than the other two. So the intuition here is to say, all right, I'm going to start like before. I'm going to divide into 2 different regression problems. But let us do the following. Say I have many more controls than treated. I am going to estimate the control response function. I'm going to estimate the expectation of y given 0 given x. And then I'm going to do an imputed individual treatment effect. Because I observed treated. For the treated individual that I observed, I don't have to estimate anything. I just observe what you had in treatment. I take my imputed control observation from them, from this regression estimate here, which I might be able to do very well if I have like hundreds of millions of observations here, right? And then I'm going to estimate the conditional average treatment effect off of this, taking an average over this. I'm going to do that, right? I'm only going to do it one way, right? So as an algorithm, you can do it this way. I'm going to do like estimate the response function. Everything in blue is like thing I'm estimating, right? It could be random forest. It could be whatever, right? Do the impute. All I did is just take the last slide. I just replicated here. But I could go the other way, right? I could take all my treated observation. I can estimate a treated model too, right? And then I can, for my treated observations, so then I estimate a treatment model. So that for my control observations, I can take your observed control, impute my estimated control, and estimate the conditional average treatment effect for them too. Right? You see what I'm saying, right? For everybody in treated, I can like go impute what you would do in control. For everyone in control, I can go impute what you did in treated. I get 2 different estimates now of the conditional average treatment effect done this way. And I can weight them. There's various different ways I can weight them. I can make them one way in which I get a doubly robust estimator, right? I can weight them another way, which is this, which is I just weight them by the propensity score, which performance written here is not going to be doubly robust, but I'm currently thinking of experimental data, so I don't have to worry about it. So I put the weight in where my model is easier to estimate, right? So if I have an infinite number of controls and the limit, well, I'm only going to put all my weight on that model, right, and not on the treatment model, right? So that's the game. So when you do this game, you can get like these fun things. You can get optimality results under that model, Minimax results. You can also play this game that you have lots of data. I still have to estimate, but I can imagine estimating the social experiment. I can estimate the conditional average treatment effect for the full data. I can estimate using the t-learner and assume that's the truth. Like you estimate 2 separate models. I just assume that's the true model, right? You see? And then in finite samples, I can sample from that. And I can say, how do the different estimators work in finite samples? Assuming on my full sample, I estimate the t-learner. So this is the correct model, right? Because I'm literally sampling from that model, and I estimate the 3 different learners. And even though the t-learner, which is this line, is the true model, and this is training sizes, so this is 30,000 observations. Even at 30,000 observations, it still has the worst mean squared error, even though it's the true model. The reason is, in this sample, there's 2 things going on. In this data, you have very unequal sample size. So the X-learner, it can exploit that. The S-learner does this very weird thing that the mean squared error pops up and then starts going down slowly. Eventually, as the data gets very large, the mean squared error of this thing is going to go down and down and down. But they all will go down. Then what happens with the S-learner, why its mean squared error goes up is it gets more data. There's an important lesson on what's going on. If you look at the variance and bias separately, is that its bias when you don't have much data is quite high because it never spits on treatment. But that's OK. Its variance then is quite low. As you get more data, it decides I'm going to split on treatment because treatment is meaningful, but it's really bad at it, right? So the mean square error blows up, right? So you get this variance thing, and then eventually it starts like behaving better. But X always in this case behaves better because it's a very unsampled data, right? The simulation's like not made up in the sense like I assume the t-learner is a true model, but I have an unbalanced sample, so I'm going to exploit it. The other things that happen in finite data in this transphobia experiment, this is not simulations, like just the actual data. In the actual data, in the actual paper that came on Science, the t-stat for the average treatment effect was over 3. So well-powered experiment. Mostly it's well-powered, not in this case by its sample size, but the graph systems were very good at collecting very powerful prognostic covariates, right? So the R squared of Y0 on the X covariates is like 0.8, right? So that's giving you 5 times the sample size. Because of the covariate adjustment. So if you run the X-learner through it, it looks like, hey, the black line is just the simple difference in means estimator. For the average treatment effect, it looks like that's there. You see treatment effect heterogeneity. In this case, because it's an equal samples, the minimax rate for this and the t-learner and the S-learner should all be the same, right? This is what the X-learner looks like. Here's a t-learner, right? Same data. It's like massive spread now. right? Because you could intuitively think what's going on. I have these two separate models I'm taking difference of. OK, that has its features. More disturbingly, here's the S-learner, right? Remember, this is like an average treatment. There's the difference. It's not even centered on the difference of means. It's like way off. And it's a well-powered difference of means estimator. And it's just shrinking towards 0 in a very strong way, right? So even in a sample size, in this case, this is not a massive experiment. It's a sample size of 1,000, but you have like the covariate adjustments. It's giving you extra power, so you might as well think it's about 5,000. It's like sample size is small enough that if I start going off estimating the conditional average treatment effect, depending on which model I use, we all have the same minimax rates. You have this massive difference back and forth on what's going on. And that's like disturbing. And once you know that, then you probably should say, I don't really believe your confidence intervals in any way, shape, or form, right? Because whatever the bias of these estimators is, it's not gone away yet, right? It's quite extreme. You can see these in simulations as you start doing it. The setting is from Vogger and Athey, and this is like a complex setting for the treatment functions. And you can see this is causal forest. Here's the S-learner. Here's X. It happens to do well here. The base learners make a difference. This is random forest. This is Bayesian regression trees. It's a Bayesian forest. It does a lot more shrinkage. So when that shrinkage is good, it works quite well. When it's bad, it works badly. And as you can imagine, this is the no treatment effect regime. What's going to do well when there's no treatment effect? It's going to be the S-learner. It's the green line. It does much, much better. And then some of these resist confounding. These are the non-doubly robust estimators, but they still will resist confounding. And then the base learners make like a massive difference between the random forest and BART, right? OK, so the way to think about it, if you want to talk a little bit of theory, then I'm going to run out of time. So I think I'll do the theory, I'll do one other thing, and then I'll run out of time. All right, OK, to set up some of the theory, so we'll say that, OK, so my treatment is just Bernoulli. I have Y0 and Y1. They're like this. And I need some regularity conditions on tau to get like good rates, right? The way to intuitively think about it is imagine the treatment, that Y0 could be very, very complicated, right? Because I'm just predicting outcomes of control. In most settings, it's a very complicated function. And I get many, many W's. It's not sparse in my experience. In most data sets, someone's going to say, I'm going to estimate your control function. I'm going to assume sparsity. That doesn't happen. The conditional average treatment effect is often sparse. The conditional treatment effect is often very simple. Remember the Laplacian distribution I showed? That's often 0. That's very simple, right? So if there's any sparsity or smoothness on the conditional average treatment effect, I'm going to exploit it in the X-learner because I have a separate step for that. The other thing, the other way it works is if I do cross-fitting and a whole bunch of dances, the way I estimate Y0 and Y1 and then the Kate estimate, my errors for Xi and Xj become uncorrelated because I split my data up, so I make them do it, right? So the easiest result to get, it's the one in our first paper on this, is that we assume ignorability, which is a selection of observables, which is very common. Imagine that the true treatment effect is linear, right? And then we're going to make this Lipschitz smoothness on mu0, which is my control function. And I estimate the X-learner and what happens, right? So all right, so I'm going to achieve the parametric rate in n, right? But then if I assume, and then at this point, all of everything we talked about will hit that rate. The S-learner, the T-learner, causal forest, the list goes on. It's a very easy rate to hit. It's not very hard, right? So if we assume there's many more control units than treated units, however, we'll get the parametric rate back, right? And the reason is, OK, we're going to do a bad job estimating the controls. Everyone is, because it's a very complicated, rough function. But if the tau estimate, the conditional average treatment effect, is linear because of that next stage where we combine it, well, that I can hit the parametric rate for, right? After a paper came out, Foster, and I always mispronounce this person's name, and I think Foster's a postdoc at MIT, they gave a more general result for our estimator, particularly a doubly robust version of our estimator, which I didn't list in the slides in our paper. And they use the same tricks, everyone's very popular, under name and orthogonality, which basically says we will hit the oracle rate, i.e. that if we had the true propensity score and we had the true Y0 model, we would obtain the same parametric rate as that. Now, it sounds cool, but mostly everyone's proposed method does this, because it's sort of like the filtering of the journals. You have to have this property, or people are not going to accept your paper. But most methods propose obtain this minimax rate, but they don't. And this Oracle property, their finite sample performance is like vastly different, right? Like I just don't think minimax rates are doing a useful thing for us in this problem, right? And then the thing I'm going to end with is like it's a separate paper by Soren, Bradley Studies, a student of mine, 2 undergrads, and Peter Abil, who's a roboticist at Berkeley. And we do the X-learner, except we do it with a neural net. The reason is the problem with the X-learner is, and you just think about it conceptually, I'm going to estimate the conditional average treatment effect model. I'm going to estimate a model for Y0 and Y1. But I'm not telling my models for Y0 and Y1 that I'm going to eventually estimate the conditional average treatment effect, right? So they're going to go off and chase really good estimates for Y0 that they probably shouldn't be, right? Because it's not going to matter when I go to the next step and take the difference, right? So what are neural nets good for? I can like create layers and just project information back, right? So the one thing you could have done in a neural net that's very straightforward is to say, oh, I'm going to take my conditional average treatment effect model. I'm going to back propagate from that to my Y0, Y1, and to my data, right? You're actually like not doing that. If you do that, what ends up happening is you end up actually under adjusting the data. And this is the problem that ends up in causal forests, which is there are covariates that the conditional average treatment effect is not a function of, but they're very useful predicting Y0. And covariates that are useful predicting Y0, but are not interacting with the treatment effect, are useful for just reducing your mean squared error, right? So you want to like get those. So what you do here in this complicated game is to say, hey, I created a neural net with a whole bunch of different heads, and some of the heads are going to be I'll go to the algorithm form because I think it's a little easier. Some of the head is this is the control. I'm going to create a network for the control to predict my y-obs, right? I'm going to update a network for the controls to predict my y-obs plus my treatment effect, right? And then I'm going to update a network to go the other way. I'm going to do the separate things for the controls, and I'm running for the treated. My mistake. And then the thing about the nets that we have no great theoretical thing for is this. What happens here is the same thing that happens to GANs. Like if I'm setting up a GAN, like people don't like touching GANs because when it works, and you nudge it a little, it blows up. The reason is the adversarial learner and the thing that's generating the models, they have to like progress they have to co-evolve, right? If I start a GAN with a very strong and a very good discriminator, it doesn't go anywhere, right? You get this thing that the discriminator's got to be bad enough that it's a good match for the thing that's generating the model, and they get into equilibrium, and it kind of works. That's kind of like the hocus pocus for making GANs work. That if you start touching them, you get out of that balance, you will end up a very terrible GAN. A similar thing happens here, right? Because there's no direct backprop through, is that you got to co-evolve the model that's for like Y0, Y1, and tau, right? Which is the conditional average treatment effect. And they kind of like learn together in a sense that, oh, this is a good piece of information to exploit for X. For Y0, was it a useful thing to exploit for the conditional average treatment effect or not? So this gets into a very funny thing, trying to theoretically analyze this thing as a comical exercise that's not going to work quite well. And what's going on, the same thing that makes it work, and it works better than the X-learner in applications, is the same that makes GANs work, which is a little hard to analyze or think about. I won't do that data. All right, so there's all these transfer learning things that now come up. I have a whole bunch of different experiments. I want to learn from one setting to another. People could do Bayesian shrinkage, but now it's the modern age. I'll turn this into a transfer learning problem. I can warm start a neural net from one experiment to the next and see what I learn. More generally, we expect a lot more from experiments than ever. One of the things I would ask, my personal view, is we spend millions and millions of dollars running randomized experiments, right? When we do that, we want to protect the type 1 error rate, right? That's why we do it. If you have a randomized experiment, I would ask that you don't then do something that undermines the type 1 error rate, because that's the one thing we know how to control, right? In observational study, there's different asks, and that's like hard enough to do. Power for the conditional average treatment effect is a very serious concern. And power then gets related to hyperparameter tuning, because I don't know what ground truth is. I got to estimate that, and that becomes a very, very hard thing. And then the methods have become so complicated, they've run so far ahead of our theoretical understanding, right? That the only thing we kind of have to pull back is you validate on actual data. But it's hard because our estimates are much noisier than we would like. And the bias is pretty bad and hard to control. All right, so we'll stop there. Oh, and these are my co-authors of the various papers I talked about today.
Okay, we have time for questions. Why don't you call them?
Sure. At the back.
So you mentioned that both or all X-learner, S-learner, and T-learner, they all sort of achieve the minimax rate. So my understanding is that the convergence rate will depend on the smoothness of the function. So when you say they hit the minimax rate, are you saying they hit the minimax rate that depends on the smoothness of Kate, or is it the worst of the two potential outcomes?
Okay. So if the samples are not unbiased, balanced, so they have the same balance, and I'm not going to, so they're not imbalanced, correct? Excuse me. And I'm using the exact form they're going to do that. They're going to hit the worst of y0, y1, just in the very usual sense. Right. Now, there's other things I haven't talked about, which lead to kind of a double robust estimator. Like it starts from a transform model, which I can take my y. If you know, it's also a thing. I have an unbiased estimator, an experiment with one person. Right. What's my unbiased estimate of the estimate for one person? Say it's in balanced experiment, coin flip. Oh, it's like two times y if it's treated, and minus 2 times y if it's control. I literally do that. I transform my y's that way. And now I'm directly targeting Kate. And now its minimax rate is going to depend on the smoothness of that function. The problem with that thing is, if I go off and do that, I don't get to exploit gains from covariate adjustment. Right? So I first residualize my data, and then I do the transform, then I can do it. And then there's a bunch of different estimators to try to exploit that. R-learner can do that, yes. Now, R-learner does that, but it has now assumptions on the treatment effect, linearity of the treatment effect model. Right? There's no free lunch now. Right? And then also in observational data, now it's depending very crucially on the p-score in the denominator. So what's happening, it's the same thing with inverse probability weighting. When is it good, when is it bad? Hey, if those probabilities get close to 0 or 1, this is really bad behavior. That's one thing for the average treatment effect. For the conditional average treatment effect, in randomized experiments, I estimate things close to 0 and 1, just because they're random during the data, and I gotten enough covariates now, right? So that will hit. I can get. See, optimality results are not hard. We're good at proving things we're incentivized to prove. Right? Does that? That was a great question on that. There was another hand back there, up there.
Yeah. Do you have any packages that you'd recommend?
Packages for what? For the random forest that I talked about, it's online. It's in the forestry package. It's on GitHub. You can get it. The other thing that package does that I like, it's the fastest version implementation of honesty that I know. It's very fast. We also in that package do online ridge, which is what happens with forest. It's not so good. I didn't want to talk about it so much. It's like more important than the S-learner, turn-learner, and X-learner is just these pure algorithmic things, right? What does a random forest do? It's like the modern world, right? The algorithm kind of wins. It's like, what does it do? It's like, oh, I'm a random forest. In my forest, my bottom, my predictor is just a leaf. It's the mean of the leaf, right? But say there's a strong trend in there. Well, it's not very good. It's not going to exploit that. So what we do then is do ridge in the bottom of every leaf. Other people have done that before. The hard part is, and we do an online ridge, that when the random forest does its splits, it knows it's going to run ridge. So the splits are optimal, knowing that it's going to run a ridge in the bottom leaf. You see what I'm saying, right? At the bottom, it's not like a mean, but a whiteboard. I don't have ink now. I won't do it. But you like if there's a trend in the mean estimate's going to be bad. It's going to estimate a ridge regression on that. So if there's a trend, it's going to capture it. Which is to say, what's very hard? What's a function that's very hard for random forest to approximate? Just a line. This will do it then. Or say it's a v. See the true function's a v. What should the random forest do if it can do ridge? How many times should it split? Once. So we'll split once, and now estimates 2 straight lines. That's what it will do. which is the correct thing for it to do. Other implementations are not this clever because they don't do the online ridge and they don't test, because you can think of it computationally, you're adding this extra polynomial time term, right? That it's very hard. It doesn't, like if only at the end you run ridge or lasso and you don't build it into the optimization, it's going to oversplit and then run the ridge. Anyways, that's in that package, forestry. It's on GitHub. You can look at it. There's many other packages now. You asked for me, that's the one I'd give. In these data science challenges, the BART does quite well. So you should look at that too.
So do you try to control for sample size in treatment versus control? And if you can't really control for equal sample sizes, and you're really in a situation that the control is 10 times or 100 times more than your treatment, what do you do with that control?
Well, I mean, if someone told me you have 100 million observations, you get to assign them whichever way you want to maximize power, I'm going to obviously tell them to do an equal sample split. But that's not the choice. The choice is you can have 100 million controls, and you have 1 million treated. Do you want 1 million controls or 100 million? It's not a good answer to say, give me less data, right? No, it's like, give me the 100 million, and then the X-learner will exploit that data and use it, right? That would be the answer. That was like the thing that was motivating that, right? Yeah.
Also, X-learner tools like a more medical sense, like a competing risk or hills.
People have used it in that setting. There's people using it in drug discovery firms. I have no. I used to do quite a bit of medical stuff. I don't currently. I have not used it on a lot of medical data to have a thing. Like most anything else in life, it will depend. The problem in the medical setting that usually happens is they have high dimensional covariates, and their experiments are quite small, right? So if anyone actually wants valid inference, it's going to be tough, right? It's going to be quite tough. As I said, the sample sizes would get quite large. Like in the get out the vote experiment I talked about, the inferences are pretty good because the reason is you have like 230,000 observations. You have about 6 covariates, 7 covariates. Most of them are discrete. So guess what? At the end, it just becomes like, oh my God, at the end, it just becomes like a density estimation problem. Any random forest is going to do pretty well on this. But that's not what the medical setting looks like. So I have concerns about what this happens. It does in small sample sizes. Where it will probably work well, I have these older papers where I have a randomized experiment and I have a large observational data set, right? There's one on pyramidal arterial catheterization, which is monitoring device in the heart. You have the randomized experiment, which was like 500 people. It's a very important experiment because we put this in people who spend $2 billion a year on it. It turns out it actually has no treatment effect. It's zero. I probably shouldn't spend $2 billion, I should say, on it, and with a B. But we have an observational data set that's 20,000 people, so you should probably exploit that in ways which we can talk about offline, right? Let me put it this way: that 20,000 is very good at estimating you a control model, if nothing else, all right? So get your error down.
Last question, and we can continue the conversation later with a perception of the TTP area, the end of this corridor to the right.
Yeah.
You briefly mentioned using Gantz, and I'm kind of curious, what breaks, instead of using your machine learning as a predictor, use a generative or a conditional generative model to generate, essentially P of y given x and 1, and P of y given x and 0, let it rip, and what happens? Like, what doesn't work there?
That is a great question. Bradley Staddy, who's like a grad student that I work with, who's now at Vector, he and I are working on exactly that.
Because it seems like using the machine learning as a predictor is you're putting one foot in the grave before you start. It seems like you really are looking for the hidden model.
Right. So we'll see.
Okay.
That's exactly exactly what we're doing. But we're like, hey, that seems to be like a thing that we want. Now, the thing that you have to be careful about is, in that approach, we literally are going to be looking at is that the data cannot separate out individual treatment effects, right? I can give you like DGPs that the observational data can't the observed data, I should say, but cannot distinguish between. So what I'm worried about, and we're doing this and we work fine, is that the GAN, unlike in the usual setting, is just getting a very noisy information back about how well it's doing. Right? Exactly. That's what I'm worried about. But I think it's a great, I think I had naturally the exact same question we're working on right now. It's too early to have an answer. I hope it works out well, because if it would, it'd be great. Right. Thank you.
Okay, that's all the time we have now before going. Please.